Last time we started section 4. We motivated the topic of extreme values. We looked at local maxima und minima. And we looked at what we mean when we say, talk about critical points. Now, in today's lecture, it's all about classifying these critical points. Does the critical point lead to the function having a local max, like a little, mountain peak, a local min, a valley bottom, or something in between, like a saddle point or a generalization of a point of inflection? So this is the slide we finished on last time. It's called the second derivative test, and it's a generalization of the second derivative test that you would have seen at school or maybe in first year calculus. It's a little bit more complicated. No, it's a lot more complicated than the functions of one variable case. So this is the aim of today's lecture, to learn about this, to apply it, and to also see why it works. Now, if we have time, we'll also have a look at maxima and minima on closed bounded regions, if we have time. Okay. See, now you know why I leave the door open. Well, I was leaving the door open before. Anyway. Suppose A comma B is a critical point of a function of two variables. How can we determine the local nature of that critical point? Does that critical point lead to a local max, a local min, or something in between, a point of a saddle point, right? So the second derivative test is quite useful for this. It doesn't cover everything, but it's quite useful. So let's, first of all, actually have a look at the assumptions of the second derivative test. Suppose that f and its first and second partials are continuous throughout some disk centered about our critical point. In addition, suppose that the first order partials are 0 at the critical points. Okay, well that's sort of what we mean by critical points anyway, right? We find the critical points by solving f sub x equals 0, f sub y equals 0. Then, under those conditions, then we can make the following sort of conclusions. If this second order partial at our critical point is negative, and this is positive at the critical point, then f has what's known as a local max at A comma B. If this second order partial is positive at our critical point, and this expression's also positive at the critical point, then this test tells us f has a local minimum at the critical point. So let's look at the third one then. Well, let's not worry about the sign of this second order partial. Let's just worry about this expression. If this expression's negative at the critical point, then this test tells us f has a saddle point. And if this expression's 0, then, well, it tells us nothing. Okay, we can't conclude anything. In other words, we have to use some sort of different test or different technique. So there's a lot to take in there. Firstly, you won't have seen any this or this or this in the functions of one variable case. You would have only seen things like, things about the second derivative. Okay, so that's something new. The question is, how do you remember all of this? Well, this, so this is the hard thing to remember, really. You can think of it as some sort of y sub y, as a determinant of some special matrix. Okay? Now because we have continuity, f sub xy equals f sub yx. So I'm going to refer to this as the discriminant. Okay, and this D notation's pretty common. So let's look at this in practice. There's a lot to take in. We will see why it works. But let's actually look at how to apply the second derivative test. Okay, so the following example is pretty stock standard. You might see this, for example, end session. Doubtful that you'd see it on a class test, I reckon. You might, but at least not class test 1. Okay, so we've got a function, determine and classify the critical points. So first of all, let's determine the critical points, and then we'll classify them. So it's like a two-step process. Now, for this course, we're really only interested in critical points that are obtained from these two equations on the top right-hand corner, right? The f sub x equals 0, f sub y equals 0. We're not really interested in saying, oh, what about the case when the partial derivatives don't exist? Yes, that will also lead to critical points, but I mean, this function here is a polynomial, so it's not going to have any points where the partials are not defined. Okay, so let's calculate these partials. Set them equal to 0, 2 equations, and 2 unknowns. Okay, so f sub x is going to be something like 6x squared plus 6y equals 0. Oh, minus, that's right, yes, thank you. That minus sign. And so f sub y is going to be something like minus 6x plus 6y equals 0. So I've got two equations and two unknowns. I want to solve them. So okay, so this is going to be y equals x squared. And over here I'm going to get y equals x. So now all I really want to do is eliminate one of the variables. If I just replace y over here with x squared, I'll get something like this. So I'm going to have two x values that lead to some sort of critical point. Okay, so now all I have to do is put x equals 0 back into one of these equations to get the corresponding y component. Put x equals 1 back into the into the equations and get the corresponding y value. So that's our first critical point. If x equals 1, I'll get y equals 1. Okay? So our critical points are going to be zero, 0, and 1, 1. Okay, we all you know, that was the stuff that we looked at in the last lecture, right? So let's go through and classify those points now, right? So what we're going to do is see which one of these conclusions we can make by trying to apply the second derivative test. Okay? So the best thing is to just work with one of these critical points and then apply the test, and then work with the other critical point and apply the test and see what happens. So this is part 2. So we're classifying the critical points now. All right, so we want to look at f sub xx and this discriminant at 0, 0. So what's f sub xx going to be? It's going to be, we can get it from here because this is f sub x, 12x at 0, 0. That's 0, right? So is it that case? No. Is it that case? No. Well, it might be case 3 or it might be case 4. We don't know until we've looked at the discriminant. Okay? So we can definitely rule out the first 2 cases. So let's just write this out and then I'll evaluate it at 0. So this is like my discriminant. So this is going to be 0. Oh, hang on. No. Let's do it. 12x times 6 minus f sub x y. That's going to be something like minus 6 all squared. Now, I can clean that up if I want to. I don't really have to. At 0, 0, what's the sign on this going to be? Going to be negative, right? So now all we have to do is go back and go, okay, it's not the first case, not the second case, might be the third case. Yeah, the discriminant's negative in the third case, so we can conclude that 0, 0 leads to a saddle point. Okay, so let's forget about 0, 0. Let's look at 1, 1. It's just the same thing. Let's look at f sub xx at the point of interest. Look at the sign on it, and then look at the sign of the discriminant. Okay, so if that's f sub xx, it's just going to be 12, right? So that's positive. So let's go back here. It can't be that the first case, might be the second case. Okay, let's look at the discriminant and see. Okay, so we're going to have, again, we can just use this up here. So if I sub in x equals 1, y equals 1, I'm going to get 12 times 6 up here, minus 36. Okay, what's the sign on that going to be? It's going to be positive, right? So we've got a positive second derivative there and a positive discriminant. That'll be case 2. Okay? A local min. That's it. We found our critical points. There were 2 of them, and we just systematically categorized them according to the second derivative test. Any questions? That's a pretty standard question, okay? You might see something like that on end session. It's not necessarily that difficult because essentially it's just sort of taking a few partials and solving a couple of equations. Okay, so that's a good example. Okay, we would expect you to be able to solve that problem. It's sort of middle of the road. Okay, now the big question is, why does the test work? That's a good question. Okay, it seems to make a lot of sense. And going back to your comment before about the sign of f sub yy, you can play with this second derivative test. These aren't the only conditions that'll lead to these sorts of conclusions. Okay, so let me show you why it works. Okay, Taylor's theorem. We saw it when we looked at functions of 2 variables and their Taylor polynomials and approximations. So Taylor's formula says I can write a function of 2 variables as its Taylor polynomial. In this case, the Taylor polynomial of order 1 let me first say, imagine 0, 0 is the critical point, okay? It's the easiest and the notation's the simplest. So Taylor's theorem says I can write any suitable function as its Taylor series, a Taylor polynomial, in this case, Maclaurin polynomial, plus a remainder. So this line here is like the remainder bit, where C is between 0 and 1. So again, it's like, let's say, I don't know, you can, I guess in the other lecture we had a little rectangle or square here. Here was a point x, y, and then you draw the line segment, and cx, comma cy was on that line segment, joining the origin to the point of interest. Okay? Now, by assumption, we're assuming, at least in this setup, that 0, 0 is a critical point. In the sense that both of these partials at the critical point are 0. So this whole thing's 0, this whole thing's 0, and so they just disappear. So I've got some sort of simplification. Now, and this is the real crux of why it works. Let's think about this bottom term here, this messy bottom term. If that bottom term's positive, will 0, 0 lead to a maximum or a minimum? Let me say that again, or ask that again. If this is positive, will 0, 0 lead to a maximum or a minimum value of f? At 0, 0. Well, if this is positive, then the right-hand side is certainly greater than or equal to f of 0, 0. So what does that mean? Right, it leads to a minimum at 0, 0. Because f of x comma y is greater than f of 0, 0 for all x around the origin. If this big mess is negative, then the whole thing's got to be less than or equal to f of 0, 0. So that means f of x, y is less than f of 0, 0 for all x around 0, 0. Not at 0, 0. So that would be the other case then. 0, 0 would lead to a maximum, a local maximum. So that's it. That's all the second derivative test involves. What sign? How can we determine a sign on this? When do we know this is positive and when do we know this is negative? That's it. People get bamboozled about all the notation and stuff. It's a very simple concept. Okay? How can we make, what assumptions can we make that will force this term to be positive? What assumptions can we make on f at the critical point to make this term negative? Now I've written out the proof. We're just going to walk through it quickly. You can see in this bottom line, well I guess sort of this line here, that I've defined this new function q of c. Now yes, of course q depends on x and stuff, but what I really want to do is show the dependency on c. Now for c equals 0, if q is non-zero, then the sign of q of c will be the same as the sign of q of 0 for all sufficiently small values x and y close to 0. Anybody know why that's true? That's kind of a bit of a waffly statement. Anyone know? Well, it comes down to assuming the continuity of the second order partials. Okay? Continuity of the second order partials. So instead of looking at this, all we're going to do is look at q of 0 and see if we can determine the sign. We can come up with some conditions where we can make some sort of, force some sign definiteness on q of 0. Now, I've done something a bit fancy in the next line. So replace c with 0 in here, and you can see I've multiplied by this second derivative. Now, it's totally unclear why you would do that, but it comes together in the next line. If you multiply both sides by this f sub xx at 0, 0, you can go in here and factorize. Okay, I guess I've added something and I've taken something away so I can get the nice, xy. So I've multiplied through, and then I've added something and I've taken something away. Now, under those conditions, I can factorize. So look at the first term in the bottom line. It's always non-negative as long as x and y aren't 0. So if I want to look at the sign of this thing, all I have to do is look at two things. This and this. Okay, y squared, that's positive as long as y is not 0. So let's go back and look at the conditions in our theorem. You've got something about that and something about that. All right. So let's look at the first case. Under these conditions, it's claimed that f has a local min at 0, 0 in this case. Well, if this is positive, and this is negative, when I sort of rearrange everything, Q of 0 is going to be negative because I'm dividing by a negative thing. I'm dividing a positive thing by a negative thing. I get a negative, right? If f sub xx positive, and this is positive, well, I can just rearrange here and take this to the other side. I'll be dividing a positive by a positive. That means Q of 0 is positive. So then I'll get a local minimum. And the last case is where Q of 0 can change sign. That will then lead to a so-called saddle point. Now, the fourth case in here, what happens when this is 0? Well, you can kind of see where that comes from. If this is 0, then this term just disappears, right? So we can't really make any conclusions about the sign of Q of 0, okay? So in that case, you have to use a different test. So I know it's quite long, and I know some of you are going, come on, Chris, it's Friday afternoon, almost Friday night. We already had a tutorial today. Sorry, Monday. I'll edit that bit out. I do know what day it is. But what I'm really trying to show you with this approach is how stuff that we've already learnt, you can bring it all together and get a really powerful idea, a really powerful result. This is a huge result, a huge result.